So the size of your range will be equal to y, and therefore this is true. And so now we're going from left to right, and so we've proved 3. Okay, now it's getting a bit harder in general. I'd say we're probably moving out now from the junior level to senior. I mean, I called this whole course on finite group theory with the book by Barnard, which I can show you again. So it's in the Teach Yourself series. The first author is Barnard, and the title of the book is Mathematical Groups. All right. Okay, so let's do Theorem 27, and then that'll finish this lecture. All right. Now, look, in general, you will have many to ones. Having this like, this is, well, in general you'll have many to ones. So, therefore, the size of your image set or range will be less than the size of your starting set. So does that sort of seem plausible? Okay. So, like here's sort of a general case. A lot of your elements will get mapped to, right? But some may not be. Some may be loners, right? They're not mapped to. They have no pair in the starting set. That's sort of a general case. So your image set or your range on the whole will be a subset of your target set. Does that sort of sound plausible? Right? So your image set will be a subset in general of your target set, your codomain. So this is true in general. Now if that's true, if you take the size of it, the size of your target set will be less or equal to the size, done it again. The size of your image set will be less or equal to the size of your target set. Alright? Okay, so keep that in mind for a while. Now we start proving there are some interesting consequences as a result, as using this. Now remember, we're talking within the context when your two sets, your domain and codomain, are both finite, like they're finite sets. So yeah, this assumption. Alright, so in general, the size of your image set or range is less or equal to the size of your target set. And so, given that, therefore, you're familiar with this therefore sign, the 3 dots, so therefore, if your function is injective, that means this is true. So if f is injective, now this goes both ways, right? So if f is injective, you know this, right? So the size of your range is equal to the size of your starting set. So f of x is x, right? Size of. So if f of x is injective, that's true. Okay. Now this is less than size of y, right? But this is equal to, now if it's injective, if f is injective, this is this. We prove that here in part 2. Right? So substitute this with this. So put this here. So you get this. Okay. So instead of f being less or equal to y, you'll get x less or equal to y. Right? So if that's not true, like if x is bigger than y, so not this, then not this. That's just simple symbolic logic, right? So I've talked about this, I think, once at least before. so if S is true, then T, but if T is not true, so this is not T, well then not S. It's just elementary logic. For example, if I live in Xiamen, I live in China. But I don't, well, if you live in Xiamen, that's the city I live in, you live in China. But you don't live in China. Therefore, you don't live in Xiamen. Okay? So, if F is injective, then this is true. So, if that's not true, then this is not true by using this kind of logic. Okay? So if the size of your starting set is larger than the size of your target set, then F cannot be injective. Right? If that's true, that. But if this is false, this is false. Okay? Using this kind of reasoning. All right? So, so if your starting set is larger than your target set, then that mapping F cannot be injective. Now, that idea goes under a famous name. It's usually called the Pigeonhole Principle. So, the Pigeonhole Principle says if the size of X is bigger than the size of your Y, then that function is not injective. Okay? And it sort of translates into almost common sense principle. And why is it called the Pigeonhole Principle? A pigeonhole, like a little house where the pigeons can live, can stay, right, when they're not flying around. Okay, so imagine you have two pigeonholes here, and that's the set Y. And here's your set of pigeons, and I've got 3 of them here. That's your set X. X is the set of pigeons, Y is the set of pigeonholes. Now, if your X is larger than Y, so you've got more pigeons than pigeonholes, common sense, and all this proof also shows that this mapping, putting pigeons to pigeonholes, you're mapping pigeons to pigeonholes. If there are more pigeons than pigeonholes, or little houses, then that mapping F cannot be injective. Cannot be injective. And what does that mean? Well, it means that at least one of those pigeonholes has to have more than one pigeon. Right? Hence the Pigeonhole Principle. Okay, now we can do theorem 27. That's fairly quick. Rather surprising, actually. So given all this theory, now we go to an even more specialized case. So 27 also assumes that the two sets are finite, right? They're non-infinite. Their sizes are less than infinity here. And the assumption is that the two sizes are equal, right? They're equal. So the starting set size and the target set size, or the size of the domain and the size of the codomain are equal, and both finite. Right? Now, if that's the case, you come to the somewhat surprising conclusion that if that mapping, if your F is injective, therefore it's also surjective, right? And therefore bijective. Okay? If it's both. Now, if it's surjective, it's then injective, therefore both, and therefore it's bijective. Okay? So if injective, then surjective. If surjective, then injective. Now, how to prove that? All right. Now remember, these two sizes are the same now, right? It's an even more special case. Okay, let's prove it. We can, and in fact, we'll use these. We'll use parts of theorem 26 to prove 27. So in a sense, theorem 26 becomes a kind of lemma to part 27. Remember, a lemma is a kind of subproof, result taken from elsewhere, usually with connotations of being like a smaller part of a proof. Okay, so x and y are the same size. So if f is injective, we need to prove that f is surjective. So how to prove that? Okay, so if f is injective, so let's use this part too. If f is injective, if and only if, now remember these two go both ways, right? It's an if and only if. So if this is injective, then we can take the left to right case. If f is injective, then mod, the size of f is x. Okay, but look, x is y. The size of x is the size of y. So I can put size of y here. Okay? So I've now got f, size of f is the size of y, which is this. Okay? Now, part 3 is both directions, right? It's an if and only if. So if that's true, this is true. Therefore, f is surjective. Okay? So, I'll go through that logic again. Remember this, special case. If f is injective, then this. But x and y are equal in size. Okay? Therefore, this. Now, because it's if and only if it goes both ways, so if that's true, this is true by going that way. So if injective, right? So your logic's sort of like this. So if injective, it's surjective. Okay? And the other one is very similar. I'll just go through it quickly. You can probably guess that it's much the same. Alright, now this time you assume f is surjective. Right? Start here. So if it's surjective, this is true. Because this goes both ways. So if this is true, this is true. But y is equal to x from here. So put an x here. Well, then you get this. Okay? Now this too is both ways. So if that's true, that's true. Okay? So now your logic goes like this way. Okay? So if it's surjective, it's injective. And that's what Theorem 27 says. And that's the end of this lecture. Now, next lecture will be on, what will be? Lecture 10. So we're halfway through the course. And lecture 10 is about composite functions. That means functions that have parts. So more specifically, you can imagine having 3 sets like A, B, C, and having 2 functions like f maps from A to B, and then a second function, let's call it g, like fg, and g maps from B to C. Okay? So then you can imagine a so-called composite function, call it h, fgh, and h maps directly from A to C. Okay? And we'll also talk a bit about so-called inverse functions, where you, like if f maps A to B, maybe, and it depends, and we'll talk about that next lecture, you can go the other way. You can go back. You can go from set B back to A under certain circumstances. And that's what we'll talk about. So if you can do that, that reverse mapping is called the inverse. Now if you have three mappings, say with 4 sets, so A, B, C, D, so you have mapping F, mapping G, and then another mapping, then you can show those 3 mappings are associative. And there's a mapping that doesn't do anything. You could call that the identity mapping. And you've probably seen where I'm going with this. So with associativity and inverse, and you can show these composite mappings are closed, if that makes sense. And with an inverse mapping, you've got the properties of a group. So with these functions, you can actually create a group out of them with under certain circumstances. So that'll be the topic for next lecture. So till then, ciao.